We shall continue with the analysis of clipping circuits. So this is the third video on wave shaping circuits, that is clipping circuits. We shall consider the fourth clipping circuit. Now we have an input voltage and there is a resistor R1, R2 and there is a diode connected in the shunt in parallel with R2. So we need to analyze what is the output voltage when we apply a sinusoidal AC signal over here. Now in this analysis we shall assume that the diode voltage is not 0. So let us assume that VD on to be around 0.65 volts, that is 650 millivolt is the VD on. So it requires minimum of 650 millivolts at the P type for this diode to turn on. In order to have 650 millivolt on the P side, so we have to actually have a voltage which is slightly greater than the required voltage at this P time. That depends on the value of R1 and R2. So let us continue the analysis of this circuit by considering when the diode is on and off. So let us consider the circuit when diode is on. So this is a circuit how it looks like if the diode is replaced by the on condition, that is a switch, and VD on is the diode voltage when the diode is on. So we know that since the output voltage is measured across the diode, the output voltage is VD on. Next, the question is when does this condition occurs? Now we know that the voltage at the P should be more than VD on so that this switch closes. So in order to have VD on over here, so what is the required voltage at the input? So as it was told that it depends on the values of R1, R2. When the input voltage is greater than, so R1 plus R2 by R2 multiplied by VD on. Only when the input voltage is more than this ratio multiplied by VD on, then only the diode conducts. So assuming R1 to be equal to R2, if R1, R2 are same, so if 650 millivolt is the diode on voltage, we are supposed to actually have, so then this ratio happens to be, it is because R1, R2 is same and R2 is here, so we're going to have the input voltage should be twice of VD on. So if it is 650 millivolt, we are supposed to have 1.3 volt at the input voltage so that diode turns on. So when the input voltage is more than 1.3, then only diode conducts. So we shall see, of course, when diode conducts, the output voltage is VD on. So let us have a look at, okay, when the diode is off, how does the output voltage looks like? So the equivalent circuit is this. So when diode is off, now we are representing that switch by open. So this is VD on because this is the representation of the model of the diode. So this VD on doesn't come into picture because this is a representation of a off switch here. Now the output voltage is given by the ratio of R2 divided by R1 plus R2 multiplied by the Vin. So this will happen when the input voltage is less than or equal to R1 plus R2 by R2 into VD on. That is, any input voltage less than 1.3 volt, the diode is off. When diode is off, we know that the output voltage is R2 divided by R1 plus R2 into input. If R1 is equal to R2, the output voltage is half of the input voltage. So let us see how does the transfer characteristics of this clipping circuit looks like. Now this is how the transfer characteristics looks like. So we have a dotted line corresponding to the input on x and y axis, which is the reference now. So as we can see now, we have marked a reference voltage on the input corresponding to when the diode is going to turn on, turn off. So that is given by VD on into R1 plus R2 by R2, which is exactly this. If the input voltage is more than this, the diode is on. When the input voltage is less than this, the diode is off. Suppose if VD on is 0.65 and R1 is equal to R2, the V0 is equal to 0.65. That is, V0 is equal to VD on when diode is on. This condition occurs when input voltage is greater than 1.3 volts, meaning when the input is more than 1.3, diode is on, the output voltage is constant at VD on, that is 0.65. Similarly, when the diode is off, here, the output voltage is given by this expression, with R1 equal to R2, the output becomes V in by 2. So diode is off. So this will occur when input voltage is less than 1.3 volts. As we can see now, this is 1.3. If the input voltage is anything less than this, so output voltage is half of the input. So that's why you can see this blue line is having a slope half compared to the input voltage having a slope of 1. So this way we can see that when diode is on, the output voltage is VD on. When the diode is off, the output voltage is half of the input voltage. This is a corresponding waveform. As you can see now, this dotted line is a input voltage. So as long as the input voltage is less than twice the VD on, the output voltage follows the input voltage, but it is half compared to the input voltage. Now we can see this is not exactly same as input, it is half. If the input voltage exceeds 1.3 volts, the output voltage is at VD on. So this follows here, and during negative half cycle, as you can see now, if the input is minus V peak, the output is half of V peak. So this is when R1 equal to R2. So this is the waveform representation of this circuit, and this is the transfer characteristics of the circuit. So we shall see the simulation of the same circuit using LT spice, and we just come back and analyze the same circuit. Now we shall see the LT spice simulation of the considered circuit. So we have R1, R2, and there is a diode, and we are assuming that R1 equal to R2, which is equal to 1K, and we are doing a DC sweep from -5 to 5 volt with an increment of 0.01 volt. So let us run this and try to see how does the characteristics looks like. Now this is let me find how the input looks like. Okay, this is the input. Now this is the reference. Now you can see this is having a slope of 1. So let me see the output voltage here. So this is the output voltage. Now carefully observe this. So let me just move the cursor on one of the cursor on the output. So as long as the input voltage is less than 1.3, so this is almost equal to 1.3 somewhere here. Now you can see it is 1.29, which is 1.3 volt. If the input voltage is beyond 1.3, the output voltage is at 0.65. That is, you can see this is 665 millivolt. So meaning when diode is on, the output voltage is constant at VD on. That is, any input voltage more than 1.3, diode is on. So let us consider the case when the input voltage is less than 1.3. Please see this blue line. So it is having a slope half compared to the green one. So green one is having a slope of 1. So now you can see, now this indicates that output voltage is half of the input voltage because the values of R1, R2s are same. If you change the value of R1, R2, then the slope of your output voltage changes, and it will be always less than 1, irrespective of the value of R1, R2. So we shall go to next circuit and try to analyze one more clipping circuit and then do the simulation of the same. Now we'll have a analysis of this particular circuit. So this diode will turn on only when the voltage at the P is greater than the VR plus half of the input voltage. So if VR happens to be 2 volt, so the output this diode will conduct when it is 2 plus half of the input voltage, meaning, so let us analyze this circuit with diode as on condition and with diode as off condition. With diode as on condition, we'll have the equivalent circuit given by this. I can see this is the diode which is closed now. Now it is on, so being represented by a voltage source VD on. So this resistor R1, R2 and the reference voltage are there as it is. Now when the diode is on, the output voltage is given by input minus the VD on. So this is the output voltage expression. This condition will occur when the input voltage is greater than VR plus VD on into R1 plus R2 by R2. So this is exactly the diode will turn on when it is when the input voltage is more than VR plus the VD on into R1 plus R2 by R2. So if the input voltage is less than this, the diode is off. So we shall see when the diode is off, how does the equivalent circuit looks like, and what are the equivalent output voltage expression, and when does that occurs. Of course, when does this off conditional occur is when the input voltage is less than or equal to Vr plus Vd on into R1 plus R2 by R2. So this is the condition when does this occur. So this is the equivalent circuit. Now we can see diode is being represented by off. This is now off. The output voltage is given by, so Vr plus Vin into R2 by R1 plus R2. So this is the expression for the output voltage. If R1 is equal to R2, we will have the output voltage is Vr plus half of the input voltage. So this will occur when the input voltage is less than Vr plus Vd on into R1 plus R2. This is actually this ratio will become 2. So it is Vr plus 2 Vd on. If the input voltage is 2, sorry, the reference voltage is 2 volts, and if Vd on is 0.65, so it's at this is 2 plus 1.3 volts. It's around 3.3 volts. Any input voltage less than 3.3 volts, output voltage is equal to 2 plus half of the input voltage, that is diode is off. If the input voltage is more than 3.3, the output is Vin minus Vd on. So let us have a look at how does the transfer characteristics looks like. So this is the transfer characteristics. Now we can see we have this dotted line indicating Vin on x and y axis, which is a reference now. So we have a one more reference line on the input x-axis, which is indicating uh, the point when the diode is on and off. So now this is the reference voltage, which is Vr plus Vd on into R1 plus R2 by R2, assuming R1 equal to R2 and Vr to be 2 volts, and with Vd on as 0.65, this particular voltage becomes 3.3, meaning that any input voltage beyond 3.3, the diode is on. When the diode is on, you can see the output voltage is Vin minus Vd on. So this dotted line is Vin. This is the output voltage. Now you can see the output voltage always less than the input by a magnitude of Vd on. So this is going in parallel with the input voltage, but it is less by Vd on. And if the input voltage is less than 3.3 volts, so as we saw here, the output voltage is Vr plus half Vdn. So this is half the input voltage. So it is Vr plus half the input voltage. Now you can see this is Vr 2 volts and it is half the input voltage. Now this will occur at 3 volt. This is occurring at 3.3 volts. Now it is 3.3. Now the output voltages keep reducing. The slope of the output voltage is half. The output voltage at any point of time will exactly represent this particular expression, which is given by Vr plus Vin into R2 by R1 plus R2. It's exactly Vr plus half of the input voltage under these conditions. Now this way we can analyze the circuit by considering diode on and diode off. So let us have a look at the simulation and then verify the same thing. Now here is the circuit which we discussed on LT-Spice. So let us apply input voltage varying from -10 to +10 in steps of so and so, and let us see how does the waveform look like. So this is the input voltage, which is input on x and y axis. That's why it's a straight line with a slope of 1. Let us have a look at the output. Now since the reference voltage is given as 1.35 volts, when the input voltage is uh, 1.35 plus half the input voltage, the diode turns on. So now we shall see how does the output voltage looks like. Now I can see now the diode is turning on now here. So let me have the reference line. So this is on the input voltage. So let me move. I can see here the diode is turning on. It's almost 1.9 volt. So it's almost 1 point. This is the vertical value. So on the horizontal side it is almost 2 volt. At around 2.5 volts the diode turns on. So that is, so if you go back and see at what input voltage the diode turns on, it is Vr plus Vd on into R2 by R1 plus R2. So that is the input voltage at which the diode turns on. So this is the voltage at which the diode turns on here. So let us go back to simulation, try to verify the same thing here. Now you can see once it is turned on, the output voltage follows the input voltage, but it is less by VDM.